2024. And today we will have OSEAN's 14th seminar and 150th international seminar. We will study the paper on inshore-offshore sorting system revealed from global classification of ocean litter. Today, Elisa will present her studied abstract and details. Elisa, please.
Morning, everyone.
Good morning.
I'm a bit sick today, so my voice might suddenly disappear. Excuse me in advance. Here is the abstract for this paper. The aim of this study is to provide the first overview of the origin, transport, and ultimate fate of litter in the global ocean. I will go straight into the introduction because we have a lot to cover today. So a global picture is emerging of the distribution of plastic fragments on the ocean surface, characterized by great mid-ocean accumulation zones. Yet plastic floating on the surface accounts for only a tiny fraction of the estimated annual emissions into the ocean, and large-sized items are underrepresented in the trawling plankton nets commonly used to measure floating debris. While macrolitter, which counts litter items by type, is often studied, these macrolitter inventories are underused due to large part to the differences in the classification methods across studies. So this study conducts a global classification of macrolitter by type of product, where authors harmonize inventories from scientific surveys and civil society networks to create a database of millions of litter items found across 7 major aquatic environments, ranging from rivers to shorelines and the open ocean, and from the surface to the sea floor. The data are all shown in the supplementary information. Here are some excerpts from the supplementary information. Specifically, it includes information on the types of environments and data sources assembled, as well as a map visualizing the global distribution of the data sources compiled for this study. Also, as shown on the right, through the combination of datasets gathered from multiple locations and habitats, this allows authors to harmonize item categories and use relative proportions. So you can see the figure on the right for explanation. We will move to the figures. To start with, the paper introduces the items in their database. The figure shown here is the product of their analysis of more than 12 million litter items retrieved from 7 major environments globally. The litter items were classified according to their material composition, type of product, and probable origin. Each ring, shows 7 segments, each corresponding to one of the environments investigated. From the inside out, concentric rings represent material types, plastic types, and origins specifically. The relative sizes of color portions in each ring segment represent the relative counts per environment. Let's take a closer look at the figure. From inside out, the green part, or star 1 here, shows the 7 major environments, which is riverbed, shoreline, river waters, nearshore waters, open waters, deep sea floor, and nearshore seawater. Then the second ring, or star number 2, here shows the material types, which is based on the legend shown here on the left. On average, at each major environment, 80% of the items were made of plastic, followed by metal, glass, and fabric. As highlighted in yellow, the largest share of plastic was found in surface waters, followed by shorelines, and then below the surface, the proportion of plastic in the total litter increased progressively from 49% on riverbeds to 64% on nearshore bottoms and 77% on deep sea floors. We'll come back to star number 3, plastic type, later on. In terms of litter origins, takeout consumer items made up the largest share across environments, accounting to 50 to 88% of each environment, except for the open ocean, where most of the items resulted from ocean-based activities. The largest share of items originating from household and industrial activities was observed in riverbeds. Items with a medical and/or hygienic origin, widely attributed to toilet flushing, were more prevalent in nearshore sea floors. Smoking-related items such as tobacco pouches, cigarette packages, and lighters were most abundant on shorelines, even though the widespread of cigarette filters and cigar tips were excluded from the analysis due to their small size and inconsistent sampling across inventories. Figure 2 shows the top 10 litter items in aquatic environments. Bar means percentages per environment, while the darker colored areas and lines around the mean shows the individual data outputs and the distribution bean plot. The bar color also relates to potential origins such as takeout consumer, ocean and waterway, and industrial and household origins. The database assembled here provides a cross-ecosystem view of the nature and origin of ocean litter. Of the 112 litter categories used in this analysis, 10 types of products accounted for three-quarters of all litter items found globally. The top 10 products in descending order were plastic bags, plastic bottles, food container and cutlery, wrappers, synthetic ropes, fishing-related items, plastic caps and lids, industrial packaging, glass bottles, and beverage cans. Plastic bags appeared among the top 2 highest positions of the rankings of all environments, with the exception of riverbeds and open waters, both of which had plastic bags at top 7 and top 8 respectively. Plastic bags is purple color. Plastic bottles consistently ranked among the top 5 items in every environment and were particularly frequent in deep sea floors. Wrappers and packaging were abundant in coastal environments but were relatively scarce in the open ocean. Plastic food containers and cutlery were the most reported items found in river waters and were very common in shorelines. Synthetic ropes, strings, threads, buoys, and nets represented the majority of items found in open water, 61% of the total items. These items tend to be part of fishing gear that have been lost or discarded. Beverage cans were also among the top 10 litter items on seabeds, especially on deep bottoms. Glass bottles were highly common in riverbeds. Finally, industrial packaging were prevalent in river waters as well as offshore areas, both water and seafloor, probably due to distinct land-based or from the industry and agriculture and ocean-based shipping sources. Despite the presence of local datasets such as the reported on worrying abundances of sanitary litter in in urban rivers and agricultural plastic waste in areas of Mediterranean, this research's global analysis clearly points to the consumer activities as the main source of marine litter, followed by sea-based activities. Interestingly, film-type plastics such as bags and wrappers were highly prevalent in nearshore areas, while the contribution to total plastic macrolitter in the open ocean was extremely low, only 3%. Film plastic made of polymers denser than seawater, such as PET, are likely to deposit near the point of entry into the sea. However, most of the film plastic is used for lightweight single-use products and generally made of low-density polymers that float in water, such as PE and PP. These plastics can be expected to be transported long distances along the ocean surface by wind and currents, but results of this research do not support the idea of an efficient transport from land to open waters from these materials. Litter composition at the sea surface shifts from takeout consumer items near shore to a dominance of fishing-related items offshore, reflecting land and ocean-based inputs of macrolitter. You can see figure 3 for illustrative samples from nearshore and offshore areas. The recirculation of floating macrolitter into coastal environments is not in conflict with the accumulation of floating plastic debris reported in the subtropical gyres of the open ocean. Global particle tracking models agree that litter accumulating in the subtropical gyres is due primarily to the Ekman transport and surface convergence of debris into the centers of the ocean basins. However, surface transport models that account for the portion of the item emerge above the sea surface as well as the depth at which the items submerge in the mixing layer describe opposite delivery pathways, depending on the object's buoyancy. So the author's inshore-offshore sorting system of floating litter is based on two things: buoyancy and size as key features, and transport pathways of top items, both of which will create a more complex picture when other factors not included here are involved. As you will see, the dependence of the surface transport of floating debris is on its buoyant force, which may explain the segregation of litter along the ocean surface. Floating litter is sorted into turbulent conditions induced by wave and wind, with some items more prevalent to the water surface and others more susceptible to submerge into the mixing layer. Thus, highly buoyant items are more affected by the wave-driven strokes drift and windage, which results in ejection from the oceanic accumulation zones and transport to shore and beaches. By contrast, low buoyancy litter would escape the wind and waves, sweeping the ocean surface and have a greater likelihood of entering into the Ekman convergence to the Great Mid-Ocean gyres. The buoyant force of a floating item is strongly related to its volume. Thus, small-sized plastic fragments are a fundamental component of the low buoyancy litter. Previous studies have provided empirical support for the seaward transport of small plastic particles by using surface trawling plankton nets to estimate the ratio between micro and mesoplastic. Then, researchers explored the size distribution of plastic debris, ranging from items as small as 0.1 mm up to 1 meter in both nearshore and offshore waters. For all types of plastics, the researchers found that small fragments to be notably more frequent in open ocean accumulation zones, whereas large items were more prevalent in coastal waters. While plastic degradation can occur throughout the ocean surface, shorelines are singled out as an important potential source of small fragments. The degradation of plastic items exposed to high temperature conditions and mechanical force from waves breaking accelerate the cracking and fragmentation of plastic litter onshore, resulting in the generation of the small fragments that are then likely to be transported offshore. On the basis of an illustrative flow diagram of ocean litter and the relative proportions per environment, the authors propose an initial conceptual model of the most likely flows of top items as shown here in figure 4. This figure shows the conception model of the most likely predominant flows of the top litter items in the ocean. Each of these arrows hypothesize the main connections among environments, and it is depicted as pools. The contribution of relative abundance into each environment is indicated by each color based on the legend on the top left. The white portions in this environment pools account for the other items not listed in the legend. So the analysis captured the two major vertical pathways of litter delivery, which is nearshore and offshore seafloors. On the surface, the horizontal connection between nearshore and offshore pathways occur mainly through bottles and fishing-related items, which are actively transported across the ocean surface. Theoretically, a global inshore A global inshore-offshore sorting system of floating litter should result in high relative proportions of macroplastic in coastal waters and microplastic in open waters. However, this general pattern can be modified by the skewed distribution of plastic sources, size-selective sinks, and other transport processes working on smaller spatial scales. In other words, we must note that most sources of marine microplastic originate from land, which could lead to relatively high microplastic concentrations in nearshore areas. While highly buoyant plastics is transported across the ocean, the microplastic load gets reduced by the selective mechanisms of removal from the surface. And surface transport mechanisms at scales smaller than the great subtropical gyres also act on the floating objects depending on their buoyancy and size. Considering that buoyant items show a wide range of sizes, shapes, and materials, the subsurface transport of litter close to the neutral buoyancy remains a potentially important pathway of transport. Coastal areas as the major sink for macrolitters is that the coastal trapping of buoyant macrolitter along the coastal deposition of land source items made of non-buoyant materials makes the nearshore seafloor the most likely sink for macrolitter. Although there are no consistent quantitative mass measurements across environments to scale the stock of litter in the ocean, macrolitter density data scattered over the world support this reasoning as shown here in Figure 5. The researchers' analysis of macrolitter densities on the seafloor depict a sharp increasing trend from the deep to shallow areas, reaching the order of 1 item per 10 square meters on the seafloor, are closest to the shore, akin only to those concentrations measured along the shoreline. Using the nearshore seafloor reservoir to explore geographical patterns in litter composition, the researchers noted that the prevalence of single-use items were apparent at more densely inhabited latitude, as shown in supplementary Figure 7, but their proportion decreased outside this latitudinal band, where the share of fishing-related items increased. So the share of single-use plastic also decreased in the socioeconomic regions with the highest GDP per capita. Both a small population and high GDP are associated with low waste inputs from land into ocean. Thereby, researchers found a lower fraction of single-use plastic litter relative to fishing gear in areas where lower waste loading is predicted. Now we'll move to methods. For this study, 36 datasets providing counts of litter by item typology in river waters and riverbed, shoreline, nearshore waters, and near seafloor, open waters, and deep seafloor were included. Assimilating such diverse data streams poses a major threat for the comparability and standardization of datasets using different metrics such as counts per unit surface, volume, or linear distance, which could preclude absolute number comparison among environments or sometimes within environments. Thus, researchers' analysis focus on relative counts of item per environment, which is basically proportion of total counts. So the first part was to create a harmonization of category lists of litter items. The category lists used to classify litter items in the different environments and studies were accommodated into a joint master list category, which they call JML. This JML was made up of a total of 130 types of products. To create this JML, they initially used a detailed master list called DML, which has 237 categories that included all possible litter types in the data source and compiled for this study. Once a litter inventory was adapted into the DML, the 237 categories were aggregated into 130 categories to deliver the inventory in the JML format. The criteria they use for harmonizing litter classifications are shown in the supplementary table 2, which we will see later. And then next is data cleaning. Litter categories that could be adequately classified or sampled by a method were removed from all sets to increase the comparability of methods and analyze litter compositions across environments. First, they discarded non-identifiable items such as fragments and broken pieces that cannot be associated straight away with a particular identifiable primary object. Then the smallest macrolither items were also discarded because they probably were not systematically sampled in all datasets. This was the case of the cigarette filters, cigar tips, and other kind of litter items smaller than 3 centimeters. For ropes, strings, cords, and threads, researchers discarded those tangles and pieces smaller than 10 cm. Thus, the smallest item considered in this compositional analysis were the small bottle caps about 3 cm in diameter. Finally, 18 litter categories corresponding to the smallest and unidentifiable items were removed from the JML, and a total of 112 litter categories remain in the compositional analysis. The counts of litter items were treated as random variables to take into account the uncertainties and biases in the census. Therefore, ranges of counts in which the true number of items is expected to lie were used instead of single counts. A probability space for each was defined according to the litter category, counting technique, and environment as this formula shown here. You can read about the details of the formula in the journal. Datasets within the same environments were processed into account for the geographical sampling bias before developing the global rankings of items. Thus, litter counts per environment were put into 7 world economic regions, and mathematically, the proportion of the litter category L for the environment E in the region R was calculated as this formula on the top, number 2. And then the proportion of the litter category L for the environment E at the global scale combines the counts from the 7 regions is as shown in the bottom formula, number 3. Uncertainty in the litter counts was propagated to the top item rankings through the Monte Carlo simulations. This process was repeated for a total of 10,000 random sets of litter counts. The end result was 10,000 global rankings for each of the study environments. The dispersion of the outputs was graphed as bin plots to show the effect of the uncertainty on the global rankings. In the case of the nearshore seafloor, litter rankings were also analyzed at the regional level, since this environment showed the most spatially extensive sampling coverage and is where the highest macrolither loads are expected. Researchers also classified the litter according to material, shape, and possible provenance as shown in Figure 1. Each of the JML categories was associated with a specific material type, including plastic, rubber, textile, paper, wood, metal, glass, and ceramics, and others. For those items categorized as plastic material, an additional classification into rigid plastics, film type, plastic, and line was carried out. Linkages were established between litter categories related to their provenance, such as takeout consumer activity is related to outdoor consumption of convenience store or convenience food or shopping. The association between particular litter items and material, plastic type, and provenance are described more in the paper and in the supplementary table 4. A flowchart with possible connections between environments was designed according to 2 main gravitational flow directions, from the elevated inland zone to the deep offshore zones, and the vertical flow from surface to depth in the water columns. Researchers also considered the potential landward and seaward flows of floating macrolither between neighboring environments at the surface level. Thus, all flows were assumed to be unidirectional with the exception of those between shoreline and nearshore waters and between nearshore and open waters. So the 4 main entrances of litter to the aquatic environments were accounted for as inland inputs, shoreline inputs, nearshore inputs, and offshore inputs from high sea activities. The size distribution of floating plastic debris was measured in nearshore and offshore waters to test the proposed sorting mechanism by sea between the two environments. The size distribution of seafloor floating plastic was reported by Lebreton et al. 2017 as shown here. And you can check out the sampling information, net types, net sizes, frequency, duration, etc. all in this journal. To examine the order of magnitude differences between the main depositional environments, authors compiled data from all over the world and graphed it as bin plots. The ocean seafloor was divided into shallow, near-shore seafloor, deep and near-shore seafloor and deep seafloor. Raw measurements of microliter density per surface were used as reported in the original studies. This is the last slide, which is the additional readings and information. So you can check out the JOIC master list in this link here, and then you can check the methodology as stated earlier here, and this is just additional reading. I will show you the supplementary. So this is the paper that we touched on just now, and then this is one of their supplementary information, which they give explanation to all the other additional supplementary, and then explaining certain things. This is the sources that they use for this study. You can see here. This is the map for the global distribution of data sources compiled in the present study. So from this table, they tabulated this map, this global distribution. And then this is the workflow diagram through the steps of the standardization process of data sources. Yeah, correct. Data sources. This is the top 10 litter items across 7 aquatic ecosystems globally. And then this is the cluster analysis of litter composition per environment. And many other graphs. This is additional references. This is the additional Excel that they attached. It's all the JML and DML information, and you can check it out. They have data from a few places. And yes, that's all.
Thank you, Elisa. This paper contains a lot of contents, and we have supplement data, and it's important data and supplementary material. Thank you, Elisa. You must spend a lot of time. And we'll have discussion and opinion time. If you have any questions and opinions, please feel free to tell us and share the point.
Thank you very much for the presentation, Elisa. You prepared a lot for making us understand well of this paper. In this kind of compiled paper, the methodology is very important to harmonize or standardize the raw materials and data. In this paper, they used the relative count per environment as a very basic data from, they estimated that from counts per meter or counts per square meter, something like that. But I don't think I understood well about the concept, especially figure 5.
It's data per
Figure 5,
islands per square meter.
yes, it's for square meters. I don't exactly understand the width, the height of this binfold, each binfold graph. Can you, I don't understand well. Would you add some more explanation on the methodology. So relative counts means proportion, percentage.
Sonny, do you mean the vertical distribution? I mean the like y-axis. X-axis means the items distribution for items per square meter. So we can understand, I think. And vertically it is distributed. It is they are distributed vertically too, really. So I read this part, but it didn't tell about details for this distribution. I think we have to understand how to produce bean plot with like R program, something like that. Then we can understand vertical point, vertically distributed. Sonny, did you point that point? Like vertical distribution of the points.
Yes, I didn't find the details about that.
And in this paper, it didn't tell about that. They produced just the bean plot, they said. So I searched for bean plot, how to make this kind of plot with some program. Okay. Other
Okay.
case?
And one more thing about figure 6.
Figure 6.
When you see this picture, the left upper picture means high-income countries. The second figure is about East Europe and Central Asia. As you can see, there is fishing-related items occupied the highest proportion, even though high-income countries use a lot of plastics, single-use plastics. So this figure is quite interesting to me. Usually, high-income countries discharge a lot of plastic waste, but the plastic recycling or treatment facilities and system are well established. So the relative proportion of fishing-related items occupy the largest proportion, I think so. So in this figure, if you can, we try to find Korea from East Asia and Pacific. Wrappers and bags, and is it plastic bottle are the most abundant, which is very different from Korea. So Korea is quite high, relatively high income countries, and we use maybe 4 times more than Indonesian people per capita. But our system is good, quite good. So that's why the takeaway consumer items are relatively low. So that's what I thought is interesting. Thank you.
Additional comments. If you want to understand debris or mismanaged plastic waste and how much debris is released from each sector, you can, if you read Zembeck's paper, it also in the supplementary material, you can understand this kind of information. High-income country, in high-income countries, the management system, how the management system are developed for each sector, the division of this kind of countries, like high-income country and low-income country, middle-income country. The papers tells us more detail for this sector. I mean, the Zembeck's paper, 2015. Then from me, as Sonny pointed out, we have the shoreline data. I think we have the most data from shorelines, and for the most papers, the shoreline data is described items per meter. But in this paper, the graph is depicted with the items per square meter, but this paper didn't tell about that, how they select data from unit, like items per meter, items per square meter, like that. It didn't tell about in detail. Not really. So I wondered too. And however, this paper contains a lot of interesting points, like offshore, the fishing debris are abundant, and nearshore film type are abundant, and microplastic, how the microplastic are produced in the shorelines, and the microplastic will be distributed to the offshore. That is an important point. When I read the point, I thought about the microplastic formation on the shoreline and nearshore environment, especially for shoreline. So the shoreline is the hotspot for the production of microplastics. This paper pointed out that, so it should be emphasized, the point. And one more point, this paper deals with the proportion of the count because of the this similarity for the data. So that point is very important, and that's the good point, because the item is different, classification is different, and we have a lot of this similarity, and the range are so big for each data, like Koreans data and the Europeans and other countries. So they use the proportion of the item. This is a good point, I think. Actually, this paper refers and used a lot of data from other papers, so, and global data they used.
If there is no more questions, I will add some comments on the Excel file. Would you share the supplementary data Excel for us?
Other Excel.
Yes. Yes, this supplementary
You mean the
information
data or this?
this is very, yeah, this is what I want to
Okay.
talk. To make the detailed marine litter items or categories into more simpler items like JML. This table and transformation or categorization is very, very important for data cleaning and data harmonization. So to provide this information to the public, we will help for improving the capability among data sets. So this they did very well. And let's see the figure 1 of the main paper. Elisa, would you share the paper, the picture, figure 1?
The internet, I think, is disconnected. So,
Okay. Now this, yes, this figure has a lot of information as one diagram. So the first, the outer line represents material type. No, the origin. And the origin include the ICC-based categorization. So that's why one of the Nicolas Mallos from Ocean Conservancy is one of the authors, and this team used ICC data for the analysis. And the second line is about plastic type. I think this is the first classification among the global data set, which means hard plastics and film and line. And there is no further classification for plastic type, something like formed types. And the third layer is about material types, plastic, glass, and rubber, something like that. And environment. So this figure shows a lot of information, and you can compare all the data among the environmental types like shoreline, river waters, and nearshore waters. That is very good representing of their result. I would like to go to the recommendation part. Yes, overall, the second paragraph, overall, 8 out of 10 macro litter items were made of plastic. The reason is the combination of irresponsible production of single-use plastic goods, inappropriate behavior by end users, and flaws in recovery systems. So in this paper, they mentioned about the irresponsible production of companies and inappropriate behavior as well. So that point was good for me. And the lower part, the last line of the same page, litter from takeout food and beverage is often discarded outdoors after a short use. So it should be prioritized by waste management actions. So that was also good for me. And this paper has a lot of useful information and implications to learn. So it's very good time to study and read this paper. Thank you for choosing this paper. That's it.
Thank you, Sunny. I'd like to add one point. 1, 2, 3, 4, 5, 7, 8, 9. Ninth line. We advocate regulatory bans on avoidable items as the preferred action in the management of takeout items. In this paper, it means they mentioned about the MAPOR and other actions, but we should focus on the regulatory ban on these items. That is very important, I thought, when I read this paper. After use regulation or management, we focused a lot, but from the beginning, I mean, from the line, we don't use much plastics, many plastics like that, much plastics. So that point impressed me a lot. And one more point for the data, they discarded the small items because on some area, they didn't collect the small items, and in some studies, they collected, very diligently. They collected small items, but others didn't do that. So they discarded small items. I think that is very good point. And then I think we have a lot of discussion. So let's wrap up the seminar. Before wrapping up this seminar, we will fix the next seminar date and presenter. Okay, Youngju.
Can you share PPT? As I know, microplastic standard is 2.5 centimeter, but this paper microliter item 3 centimeter. Why does this paper explain 3 centimeter?
Oh, yeah. As I explained just before, macroplastic, the lower limit is 2.5 centimeter. And in some paper, they collected small items like larger than 2.5 centimeter, but other papers, they didn't collect all of these small items. So discrepancy occurred to compile all of the data. So they discarded the small items, but like bottle cap. Most people collect bottle cap, like the caps of the bottle, beverage bottle. So they included the thing that the lower limit may be 30 centimeters. And for the ropes and strings and cords, like smaller than 10 centimeters. In some studies, they didn't collect all of the, they didn't collect all of these small items like that, but other studies, they collected. So discrepancy occurred. They discarded the items. So it's different from the classification of the debris size, like 2.5 centimeter, like they didn't use that system for the harmonization of the data from many papers.
Yeah, that Youngju's question is good because I thought the same thing. And they selected ICC data set for this study. And ICC usually the size criteria, like as a bottle cap as a size criteria. But usually in Korea, we say the size of the bottle cap is 2.5 centimeters. But they believe, they say it is 3 centimeters. So I guess that's why they just mentioned the lower limit of the size is 3 centimeters. But almost is similar to the definition, general definition. However, it is not very clear definition, as you be curious about the size in this paper.
Okay, thank you. Then we will select the date of the next seminar. It's May 13th. The first Tuesday of May is, 7th of May. I'm sorry, 7th of May. Okay, thank you for the participation of this seminar. Thank you, and have a nice day.